Well, welcome. Good afternoon. Everyone can hear me fine, right? I think it's pretty loud. Okay. Before we begin, just wanted to have a show of hands in terms of, is everyone familiar with Hadoop, HBase, and Storm? Generally? Okay, pretty cool. So it's a little difficult topic to deal with in this type of format, but I'll try to do my best and finish it in time. So we're going to talk about capacity planning as it relates to Hadoop, HBase, and Storm. And essentially, before we begin, let me introduce myself. So I'm a Senior Director of Product Management at Yahoo and responsible for Hadoop, HBase, Storm, and all other big data platform products. This work was done jointly with another PM in my team. He couldn't be here, so I'll try to do my best to represent the entire Hadoop team at Yahoo. So let's talk about what we're going to cover here real quick. So I'll provide some motivation on the need for capacity planning. Is anyone here in the business of providing hosted Hadoop service for their organization or public cloud? Many. Perfect. So you guys will probably relate to this more than others. We'll talk about the big data platform deployment models at Yahoo. So we'll touch upon a little bit about these technologies and how we deploy them. Then we'll spend majority of our time understanding the resource drivers behind capacity planning for these things, these three primary deployments. We'll talk about capacity models and tools. So some math. I can't be too deep, so I'll try to do my best in terms of going through the overall math. And then finally, I'll talk about SLA management, which is some thoughts around going forward in this space. Okay? So we operate some of the largest Hadoop clusters in the world. Singh was just telling me, sitting here, we're now touching half an exabyte in HDFS, which is pretty amazing. Just helps us sort of get to say the word exabyte because we're now 500 petabytes in raw HDFS. So it's a very large platform and very scalable. Give me 1 second. I think it's advancing on its own. All right, we're back. So that scale is perhaps one of the most important reasons why we pay attention to capacity planning, because we spend millions of dollars in capital procuring equipment to support different use cases on the platform. And this, just to give you an idea of what that growth looks like, we're now supporting over 500 projects on this platform, and that's one of the primary reasons why capital planning or capacity planning is important. It's important both to support on-time launch of projects. It's also important for us, the platform service provider, in the form of managing the capital budget, managing the projects. Okay, so HBase, the multi-tenant HBase that we introduced roughly about a year and a half ago, is experiencing about the same type of growth, actually probably better growth than Hadoop. And we introduced this primarily for, I would say, high throughput, low latency random access service on top of HDFS, which HDFS doesn't provide by itself. So again, seeing a lot of growth in terms of number of use cases. Storm, which is yet another service we introduced about a year and a half ago, is also experiencing tremendous growth. So if you look at these three primary deployments and sort of think about the capital that's going into these deployments, it's immense. And that's why capital planning on a per project basis or overall platform is important. Okay, and most customers, when I say customers, it's the internal Yahoo users who use our platform. We interact with them in 4 or 5 primary different ways. The real first point of contact or discussion is around technology choices. We also look at their overall architecture for the use case, validate that against what we have to offer, understand the limitations and things like that. And then we actually move them through a phased environment. So we provide them a development environment, integration and performance environment, and then finally do the capacity planning, put them onto production, right? And provide the overall support for these projects throughout their life cycle. Okay? So that's why capacity planning is important. And when you think about the technology stack, Yahoo has assembled almost all based on Apache open source. Some of the things I've highlighted here in red are the ones that are super relevant for capacity planning. So most user would interact with the various other layers downstream through either Pig, Oozie, or Hive. And then GDM, which is the data lifecycle management software, and the proxies that we have are really to manage the data in and out of clusters. Most of the compute runs on most of it. MapReduce, at least right now, runs on Yarn. Tez and Spark are new, so I'm not going to touch upon those here in this forum. But we'll touch upon everything else, and particularly in the storage layer. HCAT is a metadata service, so it's really not a lot in terms of capital planning. And then there are underlying tools that we scale and manage based on load, so most customers don't worry about those. Zookeeper and other things. Right? So that's where capacity planning is relevant, the red boxes, and that's what I'm going to talk about. So let's spend some time here just to set stage on how we run things before we get into the meat of the presentation. So the compute clusters, we have many of those. So these that you see here, there are several of those. They all look identical, right? So they have a name node, they have a resource manager, which is Yarn, and then many data nodes. And then essentially, Pig, Oozie, and Hive, these things are actually per cluster deployments. Hive Server 2, Pig, and Oozie Server. And other things, the client half of these things are actually on the client side. So they manage the client libraries for Pig or Oozie or Hive or other things. And then HBase is its own deployment. So it's an isolated deployment. It doesn't run on the same clusters as compute. And again, there are many of these. And they're all multi-tenant. So Hadoop's multi-tenant, HBase is multi-tenant, Storm's multi-tenant. And then Storm, similarly, is its own cluster. They all of these deployments share a common network backplane, and that's why it's possible to have isolated deployments. So it depends on how your network's architected. For us, it's quite flat, so it's possible to have isolated deployments. Okay? So let's talk about, from a capacity planning standpoint, what are the resource drivers that matter across everything we do in the big data space. So first and foremost, it's data itself or storage, because it's all about data. The second, probably right after data, is memory. So you need to understand memory and manage memory pretty well as a resource. CPU is another one, and then throughput latency is what most customers worry about in terms of meeting their SLAs, and they're sort of tied. These two topics are tied to each other. So now let's get specific about these things. Now we understand why capacity planning is important for us, how we have deployed these technologies. Let's get specific about, we understand some of the primary resource drivers that you need to consider or look through. Let's talk about Hadoop, Storm, and HBase in particular, and go through a little bit of depth in these areas. So talking about Hadoop first, data is the most important thing. So storage is pretty much everything HDFS. And the things that matter there are the data upload frequency, the retention period of data, the replication factor. So those types of things drive storage requirement. Memory is pretty much the containers for map and reduce in case of Hadoop as of today. So we'll talk about the map memory and the reduce memory in particular. CPU as a resource is something that has been introduced recently in Hadoop 2.0. We don't use that yet, but we plan to use that pretty heavily because most of our clusters are now CPU bound. So that will help us quite a bit in terms of managing utilization and resources. And then throughput and latency, as I said, are the most important things. This is really about providing guarantees that if you run a job on our clusters with XYZ resources, it's going to finish in this time, right? So that's really important for most of the production customers. And that's important. So throughput is really about the concurrent mappers and reducers you would run to achieve a specific latency for a specific use case, which is the SLA that we would guarantee. Right? So let's talk about a particular use case. This is a very generic use case, and the best way to understand capacity planning is to actually take a practical use case and walk through that. So in this use case, I have a customer who has to finish his job in about 6 hours. He's processing 30 terabytes of data, 30 terabytes of data every day, and he wants to retain that 30 terabyte of data for a month. So he's loading a terabyte every day, wants to retain that for 30 days and run his jobs on 30 days worth of data. And this is what his job looks like. So it's a DAG where these 3 stages execute sequentially. The second stage has 2 parallel processing paths. And that's what this use case is about. So the use case says, okay, what do I really need? These are my constraints. So the first step here is to really talk about, for some reason the animation's not working, but let's talk about these steps one by one. So the first step is really to understand the inputs. So I talked about most of these. It's a daily job, operates on a terabyte of data every day. The data needs to be retained for 30 days. The output produced is about 50 GB, and that can only be retained for a day, or they only want to retain it for a day. They're anticipating 20% growth in data in the next 3 to 6 months, so we typically plan for 3 to 6 months. Right, so the first step is to calculate the server requirements based purely on storage, and that's pretty straightforward. So dfs.replication is an HDFS site.xml. Default is 3. I think most people run replication factors at 3. So you can calculate the raw HDFS requirement, taking 30 terabytes, convert 5 GB to 0.05, multiply that by the growth you anticipate, the retention, the default for fault tolerance, the replication factor. You get 208 terabytes of data that you need to store in HDFS. Any configuration, a typical machine, you can't use all the disk space. So in this case, I have 4 terabyte disks, off of which I can't use 4 because it's reserved for OS, temp space, swap space, all kinds of other things. So you're really left with 12 terabytes per machine. So you have 108 terabytes in raw need, raw HDFS need. Each server can support 12 terabytes. You get to 9 servers. So this calculation is based purely on storage. You also do a quick check on namespace requirement because NameNode has finite namespace. So that really is driven by the number of files, the number of input files, and the size of the files. We recommend most of our customers to be at least close to the DFS block size, which by default is 128 or 256 for some cases. And essentially, you do a quick check. Is this okay for the name node? And most cases, it'll be okay. Most of our name nodes support 200 to 300 million files and blocks or directories. Okay. So we move forward. So we talked about data, capacity planning based purely on data. Now let's look at memory. Memory is yet another commodity you need to manage quite carefully. And again, most of the things you want to understand here is your boundaries that you're operating within. Right, so the first thing so these are mostly admin level parameters. So what you need to understand is that every server will have a memory limit, max memory limit. It's not going to be the theoretical RAM limit. It's going to be less than that because rest is reserved. So in this case, for the config I selected, I am saying 44 gigs is available out of 48 gigs of RAM. Right? And then there is always a vmem to pmem ratio. So I'm not going to talk a lot about this, but you need to know that your virtual memory can't exceed physical by this multiple. And then the min and max allocation. So these are the boundaries you're going to operate your containers within. The min container size and the max container size. And you can adjust those. These are our defaults, half a gig to 8 gigs. Right? So your map and reducer will be within these boundaries. Then let's talk about task-specific container limits or what you can adjust. So you can adjust your map size, map container size. You can adjust your reduced container size. By default, they're either 1.5 gigs, 2 gigs, or something similar. Depends on your workloads. But you can adjust these for each job, right? And then App Master, also not very important, but there is a setting for that too. The one thing to understand is that you can also adjust the JVM heap size within these containers for map and reduce tasks. And what we see in many cases is that people sort of bump up one if they have memory-intensive jobs and won't talk about heap, like won't touch the heap, does no good. Or somebody will set the heap too big and there's no space for counters left. Again, the jobs will be short. So you really need to understand both the JVM heap size as well as the container size. Right? So these are really the only things that you need to worry about from a memory standpoint. Well, there are many other things. For the purposes of this presentation, we'll skip those. And then, once you have understood your memory limits, then the throughput of your job is really about the number of concurrent mappers and reducers you're going to run. And really, I think the best option for a customer is to leave that to the framework to select the right number of mappers and reducers, because it does go through a lot of logic. But if you were to just understand the number of mappers and number of reducers you would need for your jobs in general, the number of mappers will be driven by the splits in your input files. And then the upper limit for those splits would be the DFS block size. And then you can also control the number of mappers through the split parameters, so you can control the split sizes, which will drive the number of mappers. Right? By default, it will be the number of splits will be driven by the block size, and that will be the number of mappers that you're going to run the job with. The reducers are actually a little more complicated in terms of understanding, but for the purposes of your job, you can fix the number of reducers. You can select a set number of reducers irrespective yourself. Okay, this parameter doesn't quite work, but there is a high limit on the number of bytes the reducer processes. Typically, the rule of thumb is that you process 1 to 2 gigs per reducer up to, let's say, 5 to 10 gigs, but don't go beyond that. Otherwise, it produces too much load for the reducers to handle or the server to handle. Too low is also not good, because then the shuffle crossbar gets impacted, right? So essentially, what you would do is you will pick a fixed number of reducers, or given the total input bytes and the reducer size, I'll drive the number of reducers. Pig and Hive that most people use for data processing actually override these, or have the ability to override these precisely using these formulas. Okay, so they also have a max. Pig has a max, Hive has a max, and then the number of reducers is driven by either that fixed number, the max, or the input bytes divided by the reducer size, okay, or bytes processed per reducer. So once you've understood the throughput, the concurrency, and latency comes into picture, right? So how long will my job take given those parameters, given what I just went through from a capacity planning standpoint? This is the most important part of it. And the sad part is that you can't really figure this out mathematically very well. So what you do is you do sample job runs, right? And then you can look at the job logs and figure a lot of things out by making some assumptions. So let's say in the example use case I had 3 stages, right? So I ran it on only a tenth of data that I actually would run in production. And I got to a number of mappers. I knew the map size, and then the counters will tell you exactly how long will they take, number of reducers. I knew the reducer sizes I ran the job with, and then finally the time the reducers took, right? What you then do is that you extrapolate those results for your full data set. So in this case, if you look at the map and reduce, the number of map and reduce, that is the sort of the highest resource constraint on this serial DAG execution of PIG. So it's essentially, that's what's going to drive the total capacity for this project. So it took me 15 minutes in that stage out of a total of 45 minutes. Remember, these two are executing in parallel. So you have to sum up the resources for these, but the time taken will only be the time, the max time of those 2 stages. So you extrapolate that based on the total data set that you're anticipating. You put 10% markup for speculative execution just in case you fail tasks and jobs. And then you have 8 times more time now to process those, right? So you actually need less resources. So you extrapolate that, assuming you have a linear relationship which you don't always, and you don't know that until you know what the data is. You get to the total memory for maps, total memory for reduce, and get the total memory for map plus reduce, and then you knew that you had 44 gigs of memory available per server, you can calculate the number of servers that you need. So essentially, for this project, the max of based on compute and data would drive the server requirement. In my case, I needed 9 servers for storage and 8 servers based on memory requirement. My net is 9 servers for this project. Okay? And then you can actually host these calculations on a simple web tool, expose it to customers, and they can run these numbers. They can run these numbers themselves. They can upload the job logs of their sample runs, and you can really figure out the capacity for each project. It's pretty straightforward given some of those math. So, by the way, a lot of people have these questions, and I haven't seen anybody who's very clear about how to go about doing this, so I hope this is helpful. Okay, so let's talk about HBase now. Now that we understand how to size capacity for Hadoop, let's talk about HBase. HBase also happens to be rather straightforward once you understand the various drivers. So again, there are 5 drivers for HBase. Throughput is really the most important driver for our customers, and then latency, which are related, as I had said, memory. So throughput is really about the number of reads and writes per second you can perform on HBase or scans. Latency is about the read latency or write latency from HBase. Memory is really the block cache in HBase. So it's really about how much data do you want to cache. Data is HDFS in HBase, and really just about the number of records you want to store in HBase times the size of the individual records on an average. CPU is not really relevant here, at least from a capacity planning standpoint. So again, let's take a use case. In this use case, you have some shopping site, some shopping example, where you want to process 200 million records every day, and you only have 4 hours to process those, right? So you want to do it in a time window, and you're getting product updates with new pricing information for some of the products, and you're getting some brand new entries, right? So 50% of that is new products and will be written without price comparison. But for 50% of the input records, you want to run price comparisons. You have 3 separate tables, one for product, one for price, and one for offers, with each record being 3 KB on an average. Roughly, you have 500 million records in writes and about 250 in reads. Right? So that's the use case. So what do you really need for this use case? So let's run through our drivers and capacity calculations. Right? So as I said, throughput is the most important thing for HBase in our situation. So here are your inputs. And then since there are 3 tables, I have 1,500 writes, 750 million writes, reads, and then average record size. 50% of the data has to be cached, and then you have 4 hours to do the processing. Okay? So then the calculation based on throughput is pretty straightforward. So you know the total writes, you know the record size that you need to write, and then you have 4 hours to write those. So you're writing roughly 300 bytes. So throughout I have used bytes per second. Okay. Each server will only support so much, and that you need to know. So you can either run YCSB performance benchmarks, or through other means. You need to know what is the throughput that each server can support. So let's say if each can support 45 megabytes per second, your requirement is 300 megabytes per second. You need at least 7 region servers just based on write throughput. You can run the same calculations on read throughput. I have 750 million records to be read. I have 3 KB record size, 4 hours to accomplish. This is the average rate at which I need to read. Now, cold reads are only this much for this server, let's say the one I have selected, and cached read rates are these, right? So you need to know these numbers per server. You can do that through performance benchmarks on the configuration you run things at. 50% has to be cached out of this. So it's basically, this is the throughput for cold, this is the throughput for write, that's possible. So based on the cold and cached reads, you figure out that in this case, you're bounded by the cold reads, you need at least 8 region servers based on read throughput. Right? So you know your write throughput rate, you know your read throughput rate. Let's talk about latency. Sorry, memory then. So latency is related to throughput because it's embedded in the concept. Memory, again, in HBase is sort of simple. It's almost all about block cache. So let's say this is the typical configuration. I have 64 gigs of RAM, and then the actual heap size for region servers is about 58 gigs. Okay, and I'm caching 80% of my data. And then for memstore, the remaining 20% of the heap is dedicated to memstore. So memstore is in the write path, block cache is in the read path. Total records, I know the record size. You know exactly how much data has to be served through the region servers, right? And then you also know this we calculated previously, 55 terabytes here. 50% is cached. So the one that's served through cache is about 0.28 terabytes. The LRU that we use, there are other caching schemes recently introduced, but we use LRU. You can only use 85% of that. Rest is reserved for different types of things like catalog tables, Bloom filters, and etc. So you take that 58 gigabytes of heap, 80% for block cache, 85% loading factor for LRU, you get to 40 gigabits, right? So basically 28 had to be served. Each can serve 40. You need 7 region servers based on how much you want to cache. So you understand your calculations based on throughput. You understand your calculations based on memory. Now let's talk about data, which is also straightforward. So almost everything you want to calculate. So these you know. They are most of them in settings. So these are repeated from the previous slide. Region size here is 10 gigs. After that, regions will split. Memstore is 20%. I know that. The flush size is 128 megabytes, and the replication factor for HDFS is again 3. So what you want to figure out is the data that is served through these tables in terms of raw HDFS. So 55 terabytes were previously calculated, served. Replication factor is 3, so the raw data is 1.65 terabytes. Then what you want to calculate is the raw disk space to JVM heap ratio. 10 gigabits is the region size. 128 is the flush size. 3 is replication factor. This is the memstore ratio. You get to 48. Okay, that's the ratio. So you take that ratio, multiply that by the available heap, which is 58 gigs. 20% of that is to block cache. So this is the disk. This is the data that's going to be served per region server, right, through disk. So based on the disk requirement or data requirement, you need 3 region servers. Right, so essentially you're going to take a max of those to figure out how many region servers you need for this use case. Okay? And then similarly, you can build tools that can host these calculations to get some. Now these are rough numbers, right? These are not precise. These don't make performance tuning or other types of utilization improvements you may bring in redundant, right? Those you still have to do, but these are the starting points for your capacity. Let's talk about Storm now, which is the third deployment that sucks up capital, right? So there are only 3 things that suck up capital in the big data platform right now: Hadoop, HBase, and Storm. So Storm is all about throughput, number of messages per second that you can process for a topology through a set number of workers on a set number of nodes, which are called supervisors. The topologies are built with spouts and bolts, so we know all that. Okay. And memory and CPU are somewhat relevant here. So memory is about really the sizes of spouts and bolts, and then the messages and tuple sizes that you want to process. CPU is again about number of messages you could process. So what we're going to do, since it's all about throughput, we're going to look at throughput versus memory and CPU together. And then latency is embodied in these concepts for Storm. Storage is not relevant for Storm. Okay? So since it's continuous processing or stream processing, let's take an example use case again. I have a topology where I have a spout that reads something from HBase and then processes it in 2 bolts, bolt 1, bolt 2. So bolt 1 actually builds an index and stores it back in HBase. Bolt 2 actually forwards that index for serving. Okay? Let's talk. So you need to know some information at the supervisor is the server, the node in Storm. Some information at the supervisor level. The first thing you need to know is that the buffers, the message buffers for workers, which is the actual process responsible for processing your topologies through executors, which run tasks for either spouts or bolts, are separate from the executor queue sizes, right? So you have some adjustments for performance that you can make through these. So in this case, the incoming queue size is about 8 messages, 1024 tuples, 1024 tuples, 1024 tuples for the executor in and out and worker out, for the spout out. Slots is what each executor runs on. So for us, we usually use dual hex core machines. So we have 24 hyper-threaded cores of CPU, and each forms a slot. Slot is what the workers would listen, the executors would listen on, the ports. So basically, you have 24 ports in essence. And since I said we have made Storm multi-tenant, there's a multi-tenant scheduler that provides user-level isolation, so each user can reserve a set number of nodes. And then within that, you can then also dedicate resources per topology, just like isolation scheduler works in Storm. Okay. So let's run through a calculation. You ran your job and you saw that you were processing 1,000 messages per second. Okay? But you want to process 8,000 messages per second. That's the desired throughput. So you actually need a factor of 8 in your executors. So I had 1 spout, but you now need 8 executors for that spout. The first bolt that I ran used 5 executors, but you actually have to use 40 executors. Now Storm scales pretty linearly. So these assumptions hold. For second bolt, I also used 5 executors in my sample run, but now I need to use 40. And I know the number of tuples I've observed that the bolts are processing. So essentially, instead of 1 plus 5 plus 5, I'm in need of 8 plus 40 plus 40, or 88 slots. Each executor is a slot. Now, executors can run multiple tasks. We run 1 task per executor. So the number of supervisors or servers that you need based on this is 4, right? So it's basically need 84. You have 24 slots for executors available per server. So you need 4 servers. In terms of understanding the CPU interactions for your processing needs, that's also pretty straightforward. So I observed through some tool, JMap or JStack, my CPU usage for the run I made, right? So I'm using 4 physical cores. If you assume equal CPU distribution for spouts and bolt executors, you can figure out the number of cores, exact number of physical cores each executor is utilizing. And then you extrapolate that to your target, right? So it's basically 4 by 11. But I need 8 times of that and 40 times of that, as we had done previously. You come to a set number of minimum cores that you would need to at least get that throughput. So you're essentially looking at 3 servers based on CPU load in terms of how many messages per second you need to process. You also need to look at memory, and essentially those calculations are also pretty straightforward. You have 8,000 messages per second that you want to process. The incoming messages are 3 megabytes. So you essentially, the spouts are looking to process about 24 gigabytes per second. You have these many tuples that you observed, but you need 8 times of that, as we had done previously. Average tuple size is this. So you essentially come up with the total for both bolts, the total GB per second you would need. You sum all that up, that's your GB per second requirement, right? Each server has 42 gigs of RAM available, but you need 44, so you need at least 2 servers just based on memory utilization. So net-net, you looked at the number of messages per second requirement, the throughput requirement, the throughput that you were observing, you looked at the CPU usage and the CPU usage you anticipate when you scale that up 8 times. And then memory, again, when you scale up your observed memory usage 8 times, as in this case, you basically come to a number of supervisors that you would need to execute your topology at the desired target message per second rate. Okay? Same concept, you can host these. Again, the animation is not working, apologize. I did something on the deck, I guess. So you basically host these calculations in a simple tool so people can figure out what are their requirements and what would they need in terms of, or how much server would they buy initially at least. Okay, and then the idea is, so again, apologies, there was an animation. So you do need to manage the SLA on an ongoing basis. You can't just say you've dedicated so much of capacity or resource for these use cases and be done with it. You actually have to go look back. So there needs to be a feedback loop into managing that capacity pretty carefully. So I had some examples of queue usage here. So in Hadoop, we use capacity scheduler where you can actually tune queues on an ongoing basis in the parameters of the queue to manage capacity pre-wall. You can use some standard tools where you aggregate all your logs in a warehouse, run Hive queries to analyze what's going on, do performance tuning on that basis. We don't really have good tools for Storm yet, but Storm UI is pretty descriptive, so you can use that in terms of understanding what's going on with your topologies and the resources they're consuming, the types of latencies you're getting, both the completed latency and executed latency. So Storm UI can tell you quite a bit, and then you can add additional metrics. We're actually doing that right now to Storm. And then going forward, all of this is expected eventually to run on the same clusters. As I said, we actually run HBase and Storm as multi-tenant service, but in isolated deployments. So really the enhancements we made to HBase and Storm are around this concept of managing multiple tenants on the same cluster, just as Hadoop does. But they're not all run on the same cluster precisely for the reasons I mentioned. You want to make throughput guarantees. You want to make latency guarantees to customers for all of these three. And if you're all sharing the same compute cluster without good isolation, you're going to run into issues in terms of those observed throughputs. And if your network allows you to keep them separate, so be it, right? It's easier. Multi-tenancy then allows you to manage all that on the same cluster. But going forward, we're going to try and move all of that over on the same or common infrastructure. And then Yarn lets you do that, by the way. So for now, we have Spark and MapReduce run on Yarn. We have POCs on these to run on Yarn. And then the other ones can also run on Yarn. We haven't tried those. And then there are a number of things that are going on that will impact these calculations moving forward. CPU as a resource, I mentioned, container reuse in Yarn, Yarn support for long-running jobs, other potential resources you could manage. Right now, Yarn only manages memory. The CPU one is recently added, which we don't do yet. Test can change things, Spark on Yarn. We haven't done that, the calculations yet. Very memory intensive, by the way. And then we haven't tried the other newer caching schemes like the slab cache or blob bucket cache in HBase 90. I think some of this is in 94, otherwise in 96 and 98. Short circuit reads will impact read performance. So again, that's not incorporated here. HBase on Yarn. Again, we need to get more experience with multi-tenant Storm, and then as we run Storm on Yarn, some of these calculations will change. Okay, just acknowledgement to the team. A lot of people work in these areas. Thank you. I hope it was informative. Questions? Yeah. Yes, very good question. So, yeah. No, very good question. So if you think about what Yahoo, the Hadoop team at Yahoo does, we really pride ourselves in three areas. It's multi-tenancy, it's scale, and the third pillar, which I didn't talk about in this presentation, is security. Since your data is shared and everybody's on the same cluster, security becomes really important. So we do a lot of work in these security areas, and I believe across these 3 dimensions, we have added pluggable security models, and we have a lot of those. So the Kerberos style, the Hadoop style security is available across these 3. There are other types of security models, the authentication models we have incorporated. So they are all very secure, all 3 of them. Security has been one of the biggest works we've done in these areas, along with multi-tenancy. I mean, you can't have multi-tenant systems without security. So they go hand in hand. Yeah.
If you have to select one metric that will show the performance of your cluster, in case of Hadoop, for example.
I'm sorry, I missed the question.
So let's assume that you need to select one metric that shows the performance of your Hadoop cluster.
Yeah.
And which one would you choose?
Performance of Hadoop clusters.
Let's assume that you add 100 new machines and you'd like to see whether your workload benefits them.
I think one metric we pay very close attention to is utilization. Because SLA, if customer SLAs are not met, you would know about them. They will scream really loud. Because these are production systems, some are revenue systems. So let's say you have ad budgeting running on Hadoop, and you didn't compute the budget on time. You kept delivering ad impressions even after the campaign ended. It was lost dollar. So customers won't tolerate SLA misses. We know that. Utilization is, if you're deploying capital, hundreds of millions of dollars in our case, are you getting enough ROI of that deployed capital? What's the rationale for buying more servers? Why can't you utilize the existing infrastructure more efficiently so that you don't have to buy servers? That's what I mean by utilization. And essentially, utilization means across these different resources that I talked about, you're utilizing every one of them in the most efficient fashion possible. You have exhausted your performance tuning opportunities. You've exhausted your potential to improve utilization. Only then you go buy more servers, right? So one of the things that I experience when I go buy servers, so I go to the capital committee and say I need $10 million more worth of servers. So they will say, why? What's your current utilization? Are you utilizing what you have well today so that I can grant you $10 million more to buy hardware?
But for example, also do some configuration changes.
Of course. Of course. So that's performance tuning. That's an ongoing exercise. That never stops. Never stops. Queue tuning, configuration tuning. In fact, most of our systems, so if you think about HBase, we're actually going to do a talk at HBaseCon about that. Each of the tenants get their own configuration. Even in Hadoop, we can actually deploy specific configuration per server because we operate heterogeneous clusters. There are hardware that have been accumulated in a cluster from multiple generations. You can't apply a common configuration across all. So we customize, when we actually deploy configuration, we customize per server based on what the hardware configuration is. That's one technique we use actually quite commonly across these. So every HBase tenant will get its own HBase site XML based on, so we carve out tenants based on region groups. I think my time is up. I'm going to be hanging out at the Yahoo booth. If you guys have more questions, I can answer those. Okay, thank you.